Hello everybody, and welcome to exercise 3 on page 113 of the workbook. In this exercise, we are given a function a of x defined by the integral from -3 to x of f of t dt, okay, and f of t is the graph of the function given below here, right? And this is asking us a bunch of questions about the function a of x. Now, before we get too far into this question, it helps to remind ourselves of the relationship between these two functions, okay? Because we've got two functions going on, the f that we were given and the function a, defined as the integral of f. The second fundamental theorem of calculus tells us something about what happens when we take the derivative of this function. Okay, specifically, when we do that, we're really taking the derivative of an integral. We've talked about how essentially the derivative and the integral cancel each other out in that situation, and we get the function on the inside. Okay, so what that means then is that this function f that we're given is also the derivative of a. That's going to be a key observation as we work our way through this problem. Okay, so take for example the first question. They ask us, what are the critical points of a of x? And we have to keep in mind they're asking us for the critical points of a and not of f. Okay, so we might remind ourselves that a critical point is just a place where the derivative of a is equal to 0. So this graph that we're given is the derivative, so we're simply asking, where is that graph? Where does it have a y value of 0? And you might notice that there are a few places that fit that description. Okay, so those dots that I just highlighted appear to happen at x equals -5, 0, 3, and 5. Those are just the places where we touch or cross the x-axis. Okay, and next we come to the question of where a of x is increasing or decreasing. Okay, well, there we can remind ourselves again of the relationship between when a function is increasing and how its derivative behaves. So a function is increasing if its derivative is positive, and decreasing if its derivative is negative. So this is like asking us well, let's just do it one piece at a time. So a is going to be increasing wherever the derivative graph is greater than 0, in other words, positive. If we go back up to our picture here, notice that we're above from here to here, and again from here to here. So that would be what? -5 to 0, and then again from 0 to 3. And then there's one last stretch here where we're positive from 5 to 6, it looks like. So we're getting 3 intervals. -5 to 0, 0 to 3, and then finally 5 to 6. Okay, those are places where a prime is positive. Okay, and then similarly, a is going to be decreasing whenever the derivative graph is below the axis, and I see 2 stretches, one from here to here and one from here to here that fit that description. So let's see, this stretch would be, it sort of cuts off a little bit to the right of -6, so maybe -5.8 to -5, and then again from let's see, this stretch here would be, looks like 3 to 5. Okay, so we've nailed down where we're increasing and decreasing. All right, and then we come to questions about local maxes and local mins. All right, well, let's start with the local max part of this. So a has a local max. Well, actually, let's do local min first. Local min at. Okay, and kind of referring back to an example that we did earlier in this section, we talked about how we're going to have a local min at a place where the derivative goes from negative to positive. Because our function is going to go from decreasing to increasing. So are there any points where that happens? Well, let's see. Below to above, looks like here at -5. Our derivative graph is below to the left and above to the right, so that would be a place. And any other places like that. I see one more. Okay, at 5, we also go from being below to above. So looks like we've got two local min points. So one at -5 and one at +5. Okay, and then our local maxes, just going to be the other way around. So places where the derivative goes from positive to negative. Are there any points like that? Okay, well, back up to our graph. I see only one in this case. Right here at 3, our derivative graph is above the x-axis to the left and below to the right. Okay, so x equals 3, and sorry again for the scrolling up and down. It's kind of a long problem that we've got here. Okay, so let's see. Moving on then to part D here. This asks us about the concavity of A. Okay, so if we want to know where A is concave up, okay, being concave up is about what the second derivative is doing. Okay, so it's asking us where the second derivative is positive, and that presents a bit of a difficulty because we don't have a graph of the second derivative, but we can remind ourselves that the second derivative is going to be positive where the first derivative is increasing. We've talked about this before in a previous example. So we're looking for where the derivative graph is going up, left to right. Okay, so hang on a second, we'll scroll up and see if we can figure out where that might be. Okay, we've done quite a bit of drawing here, so let's maybe just get rid of some of this here. Okay, so can we identify intervals where a prime of x is going up? Okay, well, we certainly start out going up, so from here to there, we'd have to estimate as best as we can. What would you estimate that point is? Maybe about -2.8 or something like that? Okay, and then there's another stretch from here to here, so about from 0 to 2. Okay, and then finally from 4 to 6, there's another stretch where we're going up. Okay, so let's go back down and write down those three intervals. So -5.8 to -2.8, just roughly. Then 0 to 2, and then 4 to 6. All right, and then what about concave down? Well, that would be where our derivative is decreasing. Okay, so we'll scroll up and see if we can figure out any intervals where that might be happening. Okay, sorry, my iPad is frozen here. Ah, there we go. Okay, so let's see, we're decreasing from there to there, and then again from here to here. So those two intervals, let's see, that would be that -2.8, whoops, sorry. My iPad is launching a bit of a rebellion here. Okay, oh, wait a minute, we were in 5. Okay, yeah, again, sorry, I think I might have pressed on a hyperlink or something like that. Okay, so let's see. Was this the page? Yes, I believe it was. Okay, and so we were looking at intervals of concavity. Okay, so from here to here and from here to here. So if we kind of nail down those intervals, let's scroll back and fill those in. We're going to get -2.8 to 0 and then 2 to 4. Okay, and then finally, they ask us an interesting question in part E here. They'd like us to estimate the value of a of 0, okay, an actual value of the function. Okay, so here we kind of have to remind ourselves what the definition of a was. Okay, so that takes us way back to the beginning right here. So a of 0 would be the integral from -3 to 0 of f of t dt. And then we have to ask ourselves, how would we estimate the value of that integral? Okay, well, an integral has something to do with area, so in words, what we're trying to do is to find the area under the curve. okay, between -3 and 0. It's our choice how we want to estimate that. So let's scroll back up here. And one way to estimate area is just with rectangles. Okay, so again, I'm going to kind of clear a little bit of the clutter away here. And the interval that we're interested in starts at -3 and goes to 0. So how about if we just split that up into 3 rectangles and just do maybe a middle sum? That's a fairly accurate way to estimate area. Okay, so if we draw one rectangle that looks like this, okay, and another one that looks like this, I'm kind of using the midpoints to get the heights of the rectangles. Okay, if we can estimate the area of those 3 rectangles, that will give us an estimate of what a of -3 or a of 0 is. Okay, so let's see. You can notice from the picture that the width of each rectangle is 1. We just need to estimate the height. So that number is maybe about, what do you think, 1.8-ish? This is maybe 1.3, and this is maybe about 0.3. You might come up with slightly different numbers. That's okay. But if we take those 3 numbers, the area of the first rectangle is 1.8 times its width, plus 1.3 times its width, and then finally 0.3 times its width. Okay, we're just taking our best estimate of the height times the width of each of those 3 rectangles. And if you add those up, you get 3.4. That is our best estimate of a of 0.